Today, we are going to look at the basic principles behind electromagnetic induction. We will see how we can transform mechanical energy into electrical energy, or even light, heat, sound, whatever we want, just by moving a bar in a magnetic field. Let's consider the basic case for EM induction. We imagine here a metallic bar of length L, which has a speed v, constant speed v, and it is about to enter a magnetic field P towards the page here. Now, this bar is a metallic bar or a conducting bar. That means that it is made of positive metallic ions which are fixed and make the structure of the bar, surrounded by mobile electrons. So what happens when I move the bar towards a magnetic field? Well, I'm moving a bunch of charges toward the magnetic field. So shouldn't these charges feel a force? Yes, they do. The bar is going that way, so the charges are going that way. The field is towards the page, so the force on positive charge would be upwards. But the positive charges can't move because they are fixed, they make the structure of the bar. But the electrons can move in a metal, so it is the electrons which are going to feel a force downwards. Remember, this is for positive charges. If you want to have this for negative charges, you have to flip your hand. So let's draw what's going on in the bar when it is now moving within the magnetic field. Well, you still have the positive charges, which are getting mixed up with my pens, which are within the bar, fixed. And you have the electrons, which are now downwards. Why? Because the electrons feel a force, a magnetic force, downwards. Fm. This magnetic force will be equal to QVB, but in the case of the electron, it's EVB. So now you have your bar, and it has an accumulation of electrons downwards and some electrons missing upwards. Therefore, you have a negative charge here and a positive charge there. Well, that looks furiously like two plates. And if you have a difference of charges on the two plates, well, you will have an EMF. You have an EMF here like this, epsilon. And you have inside the bar, you have an electric field E. That would be the direction of the electric field E. Therefore, the electron will feel a force directed upwards, an electric force, Fe. I have no more space there. That force will be equal to EE in magnitude. Now, because you're moving the bar downwards, the electron is pushed, you're moving the bar to the right. The electron is therefore pushed downward due to the magnetic field. But because it's pushed downwards, it creates an electric field. So it kind of balances itself after some time, you know. Very quickly, the electron will find a kind of compromise between the two forces and find its place. When this occurs, well, I'm going to use another sheet of paper. When this occurs, you will have the magnetic force equal to the electric force. Everything will have stabilized within the bar. So I can replace it by the expressions and get rid of E. Now, if we look at our bar, we can consider this like two plates. And the distance between the two plates will be the size of the bar, L. Well, the electric field within the bar can be defined by the ratio between EMF by the length. E can be expressed in newtons per coulomb, but also in volts per meter. Now, let's replace this here. VB equals epsilon on L, which is epsilon equals VBL. Now, this is fundamental. This is the core of EM induction. That means that if I'm moving a bar, a metallic bar of length L at a speed V in a magnetic field B, at the extremities of my bar I will have an EMF equal to VBL. An EMF, well, that's a voltage. This bar is like a battery. Yeah, I'm going to draw it again. Okay, so please bear with me. Okay, now it's a little bit more clear. So I could connect this bar like I would connect a battery to, say, a lamp. Because I have an EMF here in a closed circuit, well, I would have a current flowing through the circuit. Therefore, my lamp would start shining. I just built a battery. I just converted mechanical energy by moving the bar within a magnetic field into electrical energy and then light. Now, let's consider our metallic bar moving in a magnetic field B with a speed V. I'm going to draw the magnetic field B. And let's actually make it slide onto some rails, conducting rails. I'm going to use a red color for that. You can imagine copper rails with my bar sliding on it. And here I will connect a resistor. Now, because it's moving with a speed V within a magnetic field B, it is developing an EMF epsilon. Now, this diagram is equivalent to that. I'm going to draw another one where I would have a battery with a resistance like this. And my EMF would be epsilon, which is BVL, so the current flowing through would be I equals BVL on R. Right? So I have here a current I equals BVL on R. Well, I have seen that somewhere. Yes, I see a conductor which has a current passing through it, which is in a magnetic field B. That's like a wire with a current in the field B is feeling a force normally, right? Well, here too. Let's apply the hand rule. My current is going upwards. The field is towards the page. So if I apply my hand rule, field towards the page, the current is actually the motion of the charges, of positive charges, so the force would be towards the left. I should feel a force F towards the left. Right? And F will be equal to ILB, where L is the length of the bar. So, if I have my bar with a speed V, which is dissipating energy in the resistor R, well, it will lose energy. So it will just slow down because of the force F until it completely stops. So if I want to continue having my EMF and therefore my current, I need to apply a force the other way. So I have to apply a force to keep the whole thing going. F applied. And my force applied needs to be at least equal to ILB. Well, what is I? It's BVL on R. So I can write BVL by LB divided by R. So the force I have to apply will be equal to, I need to move this a little bit, I think, V L square B square on R. So let's develop that. The force applied on the system to keep it going at a constant velocity or a constant speed is V L square B square on R. Now, the power provided by the actor of the force will be P equals F by V. Do you remember this formula? This is part of your mechanics program. So if I replace F by the applied force, I get P equals V square L square B square on R. And that is the power applied, the power given to the system. Now, if I consider my circuit, power is given through the applied force, and the current is flowing, power will be dissipated in the resistor. What will be the potential drop in the resistor? Well, it's going to be the same as the potential difference due to the bar. So, if you are more familiar with a simple circuit, epsilon and V will be equal. The power dissipated in the resistor is V square on R. So if I replace V by epsilon, again my power dissipated, which is V square on R, or epsilon square on R, epsilon is BVL, so BVL squared on R. I develop this, V squared, L squared, B squared on R. Well, look at that. Conservation of energy, yay! It works. So everything I give into the system is dissipated out. Now we know how we can convert mechanical energy into electrical energy via EM induction. We know how we can get electricity by pushing a bar within a magnetic field. We know what's going on. That's pretty cool, right? Well, in the next episode, we will look at another angle. We will discuss the idea of magnetic flux. So I encourage you seriously to check it out. In the meantime, if you enjoyed this video, please subscribe. Have a great day.